to start with formulating some sort of a shell mass balance. So far we have done shell momentum balance and shell heat balance, and we will use the equation that we have already derived, that is NA, the molar flux of A is a sum of bulk flow and diffusive flow. Now, when we think of shell, one of the dimensions would be small, which we are going to approach 0, such that we can use the definition of definition of limit and all, the first derivative. When we think of mass balance, it is rate of mass of A in minus rate of mass of A out plus rate of production of A, then I intentionally left this blank, rate of production of A by reaction is equal to 0 at steady state. That is straightforward, all of you I am sure understand this, but this is the part which I would like to concentrate some time on. If you think of some reaction which is taking place in this room, there are two ways this reaction can take place. Suppose we are referring to A as one of the species present in this room. A may get converted to B everywhere in the room or on the walls of, when A approaches the walls of this room. Now, what kind of reaction can you think of where A reacts to form, A changes to B only when it reaches the wall? Does that say anything to you about the wall? It is a catalyst. So, suppose the wall is the catalyst and A gets transformed only when it reaches the wall, not everywhere else. So, what type of an equation is, what type of a reaction is that? No, I am not talking about order right now. Nature of the reaction, one where A gets transformed into B everywhere in this room, and the second case where A gets transformed only at, let us say, the boundaries, heterogeneous reaction. So, the first case that we are talking about, where A gets transformed to B only when it reaches the wall, is a heterogeneous reaction, and the other case where A gets transformed into B everywhere in this room is a homogeneous reaction. So, that is the fundamental difference. Now, when you are thinking of formulating an equation, governing equation, which would be valid everywhere in this room, throughout this room, then A being converted to B, it is going to come into that equation as a source or a sink term. Now, which reaction would you have to consider? Homogeneous reaction or heterogeneous reaction? Repeat my question one more time. I am trying to find out the governing equation which, when solved, would give me the concentration profile of A inside this room. That is my ultimate objective. So, what I am doing is, I am taking a strip inside this room, amount of rate of mass of A coming in, rate of mass of A going out, plus amount which gets converted at steady state would be equal to 0. That is what I have written over here. But would I consider, which reaction would I consider, the homogeneous or the heterogeneous? Only the homogeneous. And so, heterogeneous reaction I am not considering at all into formulating the governing equation. So, if you look at this one, this has to be for a homogeneous reaction. Okay. So, rate of mass of A in minus out plus production or depletion, whatever may be the case, by a homogeneous reaction would be equal to 0. If it is a heterogeneous reaction, where would the effect of that would come? How do you incorporate the depletion or formation of A at the walls? By a boundary condition. Perfect. So, you understood transport process, no problem at all. So, homogeneous would come into governing equation, heterogeneous would come into the boundary condition. Now, this equation we know what to do with this, the steps, etc. The only thing is, some boundary conditions we have to understand that which are the boundary conditions that would be applicable in the case of mass transfer. What are the boundary conditions that we had in, let us say, fluid mechanics? No slip condition. No slip condition is nothing but specification of velocity at a certain point. Isn't it so that you specify the velocity of the solid, whether it is static or it is moving with a constant velocity, as in the case of flow between two parallel plates. So, whatever be the velocity of the solid, the velocity of the liquid at that point is going to be the same. So, if you specify the velocity of the solid, you specify the velocity of the liquid. What would be its equivalent in mass transfer? Concentration at certain point or at some boundary specified. So, that could be your first possible boundary condition, that you can tell it can be specified that this is the concentration at x equal to 0 or at x equal to L. Second type of boundary conditions in heat transfer, you said that at some location is receiving this amount of heat. Okay. So, if this location is receiving this amount of x amount of heat, q amount of heat, what is the boundary condition that you have used? Minus k del T del x at that location is equal to whatever 50 watts. So, what would be its equivalent in mass transfer? Minus dAB dCA dx at some x location is this much. So, instead of heat flux, mass flux at some point at some location can be specified. Similar to heat transfer, you said that a hot surface is in contact with a liquid, okay, and you are having heat transfer from this side by convection, the side which is exposed to the liquid by convection. Which law did we use? HA into T of the surface minus T infinity, that is the amount of heat loss that you are having. What is the name of that law? Newton's law of cooling. So, that is Q loss, Q convection is equal to H times A, or if I express it in terms of flux, Q double prime is H times T of the surface minus T infinity. What would be the equivalent law in mass transfer? Q double prime would be replaced by Na, right, molar, and H would be replaced by H suffix m, where H m is known as the convective mass transfer coefficient. Previously it was H, which is convective heat transfer coefficient. So, exactly like Newton's law of cooling, you can express similar law for mass transfer, where H to be replaced by H suffix m, T should be replaced by C, concentration of the species you have to mention. So, it is Ca minus Ca infinity. That means concentration of A at a point far from the location where this kind of convective mass transfer is taking place. We also can similarly say that a boundary layer forms near the surface from where convective mass transfer takes place, and generally this boundary layer is thin. So, the boundary layer, the thickness of the boundary layer would be more. Think about our discussion previously for the case of heat transfer. This thickness of the mass transfer boundary layer would be more if you have high diffusion coefficient or low values of diffusion coefficient. High, same as in heat transfer. There we saw that high value of thermal conductivity, which is the case for liquid metals, would result in a thicker boundary layer. So, same here. If your diffusion coefficient is more, then the effect of this plate would be felt at a larger depth. The last boundary condition, which is unique in the case of in the case of mass transfer, is the homogeneous reaction, which we have discussed about. The rate at which A is getting converted into something else, into B, that rate at some location may be specified. So, if the reaction is given as minus K, it is a first order reaction, minus K double prime C A. So, that means this is going to be the moles per unit time per unit area, which is in moles of A per unit area per unit time, which is getting converted into some other products. That means moles of A destroyed. One more thing that it's just a convention. This is reaction rate constant. If you have 3 primes, then this is for homogeneous rate constant. This denotes homogeneous equation and its homogeneous rate constant, and if it's k double prime, this is heterogeneous rate constant. These are by convention only. So, if I think of a wall and this is wall situated at x equal to 0 and A molecules coming in and getting transformed into some other products by, this is my reaction rate, moles of A getting transformed into products per unit area, per unit time, and suppose this can be expressed by a first order reaction like this. Notice that I have put a double prime here denoting it is a heterogeneous reaction. That means conversion of A to other things takes place not here or anywhere else, but only at x equal to 0. What is this going to be equated with? This is nothing but the reaction rate, but this reaction rate at steady state must be equal to something. What that would be? Pardon me? Is it diffusive flux or is it the total flux? Okay. Total flux at which location? Okay. So, this is the boundary condition for heterogeneous reaction that you can think of, because at steady state the number of A molecules which are coming in here, they are going to get transformed into B, C, whatever it is. If these two are not equal, then either you are going to have accumulation of A near the surface or depletion of A near the surface, which at steady state in case of mass transfer, your C A at any x cannot be a function of time. This essential requirement of steady state will not be fulfilled. So, at steady state the number of A molecules that are coming has to be consumed at the surface. So, this is a different type of boundary condition, slightly different form of boundary condition, which you will encounter in mass transfer. But the fundamental equation which we are going to use for our shell momentum balance is the one which I have written before, Na plus Nb minus whatever C dab or dab times divergence xa, or if it is just a one dimensional case, it is dca dz or dx what. But whenever you use this equation, the first thing is you have to find some relation between Na and Nb. How to find the relation between Na and Nb? You have to depend on physical process that is actually taking place. In some cases you can straight away say Nb equal to 0. In some cases you can say the whole term is 0. We have discussed that if it is sparingly soluble, etc. In some cases you would be able to say Na is equal to minus Nb such that this term is equal to 0. So, these relation between Na and Nb or the magnitude of the overall term, this you have to figure out first from the physical understanding. Only then you would be able to use this equation in your shell balance. I will give you an example of finding out why the relation between Na and Nb or the magnitude of Nb has to be evaluated first. For that we are going to deal with a system where it is a diffusion through a stagnant gas film. The situation is that in a tube, the top of the tube is open and I have a gas stream of A and B flowing over it. So, the flowing gas stream at let us say this is the flowing gas stream at the mouth of the tube maintains a constant concentration of A and B at the top, and this is the liquid A. Initially, I have B present everywhere in the system. This was closed. This was closed by a cover, and after some time, what I do is I remove this cover. A is a volatile liquid. Immediately A will start vaporizing into B. Let us say B is simply air, and I have benzene present in here. I remove this one, and benzene molecules will go into air, and it will travel through this layer towards the top. So, the benzene molecules, E molecules will travel in this direction. When I had the cover on, what was the concentration gradient present in B? When there was no evaporation from benzene from component A, what was the concentration gradient in B? 0. No concentration gradient present at all. Suddenly what happens is, number of A molecules are formed over here, and these A molecules will try to push the B molecules out of the system, isn't it so? Like if large number of A molecules are generated which travels in this direction, because you have concentration gradient, and like heat transfer, like momentum transfer, you can never stop mass transfer. If there is a concentration gradient, there will always be mass transfer. The diffusion coefficient may be small, it may take very long time to reach steady state, but you won't be able to stop mass transfer by any means. So, large number of A molecules will move in this direction, and they will drag or they will push out B molecules from this side. So, slowly a concentration gradient in B will start to develop, and as the concentration gradient in B will develop, which side is going to be more concentrated in B, top or bottom? Which side is going to be more concentrated in B? Top. So, if more concentration of B is at the top, which way the diffusive flux is going? For B? Okay. Top to bottom. So, for B, this would be the movement of the diffusive flux. In the presence of the A molecules, the movement of the A molecules will cause a movement of B molecules towards the top. Is that part clear? The movement of B towards the top at the mouth of the tube is caused by vaporizing A molecules and rapidly diffusing A molecules. So, initially this is going to be more, I am talking only about B. Initially this flux is going to be more B molecules will be moved towards the top, but as time progresses, the diffusion will also start, right, and the diffusion will increase, since the concentration of B over here is going to increase, concentration of B here is going to decrease. So, diffusion rate will increase. And how do you define steady state? Where concentration of B at any Z location is unchanged with time. How can that happen? Only when these two are equal. Okay. So, essentially you are going back to the situation which you had before you took this cover off. Before you took this cover off, the B molecules were not moving. There was no concentration gradient, no bulk flow, so B molecules were stagnant. So, if you calculate NB, which is moles of B per unit area per unit time, the value of that would be equal to 0, when you did not have any diffusion, when you did not have anything. When you take this out, you will have initially a huge flow of B towards the top, which would start diffusive flow of B back into the tube, and at steady state these two will be equal otherwise the concentration of B at different Z locations will be different. So, ultimately at the end of the process your B becomes stagnant again. The difference between the two, previously the concentration of B was same throughout. In this case you have a concentration gradient of B present in the system, but the concentration gradient, is it clear? Concentration gradient of B present in the system, concentration being more at the top, less at the bottom. So, this concentration gradient will force B towards the bottom, whereas the diffusing molecules of A will drag B along. So, in this case I have a concentration of B like this. This is high concentration and this is low concentration. It is just a pictorial depiction, it could be, the nature could be different, but this is essentially what is going to happen. So, the end effect of this is NB, NBZ, because it is in the Z direction, will still be equal to 0. So, an examination of the physical system involved would tell you something about the flux of B or the relation between flux of B and flux of A, as we will see later on. But for this specific problem we know that at steady state this condition has to be satisfied. Is it clear? All right. Now, we are in a position to go for our determination, our use of shell mass balance. So, what shell would I choose? What would be its differential dimension? dz. Very good, because A is changing, concentration of A is changing in the Z direction. So, I choose this shell, let us say of thickness delta Z, and let us say its cross sectional area is S. Okay. So, S times NAZ, this is flux of A, molar flux of A in the Z direction at some Z location, minus S NAZ at Z plus delta Z, and generation or depletion term, would there be any generation or depletion? These are non-reacting species, A and B do not react with each other. So, obviously 0 would be equal to 0. So, essentially you have d dz of NAZ is equal to 0, that is your governing equation. The surface area is a constant, so it would cancel out. S is the surface area, and what relation I have for NAZ is XA times NA plus NB minus C DAB, or rather DAB DCA DZ. This is the relation that I have, of which I have intuitively found out that NB is going to be equal to 0. So, this, can you see it? Fine, NB would be equal to 0. So, this equation would simply give you NAZ is minus C times DAB 1 minus XA dXA dz. This is from the fundamental equation of diffusion. Any question? Did you follow the steps? Okay. So, dz of NAZ equal to 0 would simply give you d dz of minus C DAB 1 minus XA this would be my governing equation. I have to integrate it twice. Use two boundary conditions, and I should be able to find out my distribution of XA as a function of Z. So, once you have the distribution of XA as a function of Z, that's what you wanted to do, the concentration distribution inside the tube as a function of position. Now, if I say that PA is the vapor pressure of A and P is the total pressure, I am repeating again, the vapor pressure of A is PA, VA to a superscript vapor, and P is the total pressure. Our system is like this. This location is at Z1 and this is at Z2. Suppose by the flow of I maintain this as the mass fraction, mole fraction of A at the top as XA2. What is going to be XA1? XA2, let us say equal to 0.1 given to us, that is governed by the flow conditions, governed by the situation, whatever condition I maintain at the top. What can you say about XA1? This is XA1. So, if you know the vapor pressure and if you know the total pressure of the system, you should be able to find out XA1. That is going to be your second boundary condition. So, this equation integrated twice with the boundary conditions XA2 known, XA1 known, you should be able to find out what is the functional form of XA with respect to Z. This is what you would like to find out. And what are the other parameters? This expression which is solved in your text that I am not going to redo over here. What would be the other parameters that this expression would contain? What are the parameters you think it would contain? Anything else that it would contain? Geometric parameter. Which geometric parameter would it contain? No, think about it. Cross sectional area, but would your distribution XA be a function of cross sectional area? Because XA is not a function of cross sectional area. XA is a function of Z. So, Z1 and Z2. So, Z1 and Z2 would be here definitely in this expression. What are the property parameters which would be there in this equation? DAB concentration and DAB. DAB is your property. Suppose this expression, which will not derive here, suppose this expression is given to you, would you be able to find out what is the rate at which the evaporation is taking place? The rate at which the evaporation is taking place. How do you derive that? dxa by dz at which location? All right. You are saying dxa by dz. Since its mole fraction, you have to multiply it with C. Okay. What else do you have to multiply it with? Minus DAB. All right. So, do you think this would give you what would this give you? Should or molar flux, whatever be the case, should it be equal to Na? Should it be equal to the molar flux? Because you have already evaluated what Na is going to be. This 1 minus Xa, that part, do not forget that part, which comes due to the bulk flow part. So, this this statement would be true if it is a diffusion only case, but it is not a case of diffusion only situation. You have previously evaluated this expression. So, this is the expression that you should use to find out how much evaporation is taking place. Where would you want to evaluate this? At Z1 or Z2, anything in between? Which one it would be? Someone said 1, someone said 2. Why anywhere in between? At steady state. So, whatever be the amount of A produced at location Z equal to Z1, the same has to be carried away by whatever means, a combination of diffusion and bulk flow everywhere else. If that is not true, then you are going to get accumulation of A inside the system, and that means concentration of A at that point would differ, which violates our steady state assumption. So, you can, so that means you would be able to see that NAZ at any location would give you the amount of A evaporated from this pool. Now, what would be the use of this analysis? I have skipped all the algebra part, the integration, all these things that you can see in your textbook. But what is the use of this exercise? Can you utilize this knowledge into something? Volatile nature of it you can find out by keeping it just in a test tube and looking at it. If it is it vaporizing very fast or very slowly? What similar on that lines, if you extend it a little more? DAB, experimental evaluation of DAB. If you look at this expression, this is the amount evaporated, moles evaporated per unit area per unit time. You know what's the area with which you are working on. Okay. So, you find out how much this has moved back over certain time. So, you would be able to find out what is the unknown, only unknown here, which is DAB. So, this is an experimental way to evaluate, to determine the diffusion coefficient of A in B. Okay. So, this way you can find out gas diffusivities between a pair of gases. So, you can have air in there, find out what is the diffusivity of benzene through it, or any combination possible. Okay. The other example that we are going to look at today is diffusion with heterogeneous reaction. So, I have a reaction going on only on the catalyst surface, and the catalyst the situation is, you know, catalytic converter in a car where a gas comes in contact with the catalyst and then it gets oxidized. So, carbon monoxide gets transferred to carbon dioxide, always to higher oxides. So, catalyst particles are placed in the converter. The gas from the exhaust of the engine comes in here, it reacts on the catalyst surface and the product goes out. So, what we are going to see is a very simplistic model of this process, and what we do in the simplistic model is we take this is the catalyst surface. Each catalyst surface is surrounded by a film of thickness delta. So, this thickness is delta. This is just a conceptual modeling of the process, it is not an exhaustive modeling. So, this is from z equal to 0 to z equal to delta. A molecules move in this direction. On the surface, this reaction takes place and the A2 molecules move back into the main stream of the gas. So, A starts at the film, travels towards the catalyst surface, diffuses towards the catalyst surface, forms A2, A2 moves back. Now, what can you see? So, remember, we have to find out the relation between NA and NB. So, in this case, it is going to be between NA and NA2, okay, both in the z direction. So, what would you say about the relation between the two in this case? my aim is to find out between to a relation between these two. For is anyone from this side? Moles of A and moles of A2, they are not equal at the catalyst surface. For each mole of A2 produced, 2 moles of A are going to get destroyed. So, one is going to be the half of that. So, Na2Z is going to be equal to half of NaZ. Is it right, or is there anything with a minus sign, because the direction of these two are different, are opposite to each other. So, this is the relation between A and B which we will have to consider. So, if I consider that one again, the equation over there, x a times N A plus N A2 all in z direction minus D A B D C A D Z. So, this A2 can be substituted by minus half of N A. So, sometimes what we have seen previously is steady state consideration would give me some value for N B. Here you would see stoichiometry of the reaction would give you an idea of the relation between N A and N B. Right. So, that is the first understanding, first exercise of first thing that we learn from this example, stoichiometry giving you an idea about the relation between N A and N B. Second is we would say that the reaction is very fast on the catalyst surface. All right. So, the reaction is very fast on the catalyst surface, and over here the flow rate is so high that you do not have we can say that its concentration of A is kept at some constant value. Right. I would like to find out what is the governing equation. So, in order to find out the governing equation, I would use the same approach as before, NaZ multiplied by S minus NaZ at S plus delta S plus reaction rate is equal to 0, right. Is that going to be the case? I will repeat again. In order to find out the governing equation, I write the difference equation first. The difference equation would be S, whatever be the cross sectional area, times NaZ at Z minus S NaZ at Z plus delta Z plus depletion of A in reaction is equal to 0. Anything wrong with that? Are you sure there is nothing wrong in it? Depletion won't be there. Why the depletion won't be there? It is a heterogeneous reaction. So, in this, in minus out is simply going to be equal to 0. So, d dz of NaZ would be 0, and NaZ from the relation that I have already written here, I can find out what is NaZ in terms of dCA, dZ, etc. So, that I will substitute in there. I will integrate it twice. Two boundary conditions that I would like to have. I would have to have. One is at Z equal to 0, the concentration of A is constant at x A 0, that is specified by the problem. What is the missing second condition? Think about what is the missing second condition in this case. I mentioned it is a very fast reaction on the catalyst surface. So, does that tell you anything about the condition? Concentration of A is 0 at Z equal to delta. if it is a very fast reaction. So, the moment A comes to the surface, immediately it gets converted to A2. So, that means the concentration of A on the catalyst surface is equal to 0. That is the second boundary condition that you are going to use. Okay. So, use those two conditions, integrate it, find out the concentration distribution of A in the film. I leave that for you. It is also partially solved in your text. Now, let us say that slightly complication will add a slight complication is that it is no longer instantaneous or very fast at the surface. That means, conversion of A to A2 is not instantaneous at the surface. On the other hand, it has a finite rate. That means, the conversion of A to A2 is given by this rate expression. What was the value of K1 double prime in the previous case? What was the value of K1 double prime in the previous case? Previous case in the sense the one that I was just talking about, the catalyst one. For I am hearing 0 from one side and infinite from the other side. Which one is true? A very fast reaction has to be K1 has to be very large. But now I am saying that K1 is finite, K1 it is a slow reaction, but slow heterogeneous reaction, and the reaction rate is given by K1 double prime Ca. So, how would my boundary condition change? My x a equal to x a 0 at delta equal to whatever at z equal to 0 will still hold, but I would like to find out what is my new condition at z equal to delta. I no longer can say that C A is 0 at z equal to delta. I could say that in the previous case only because it was an instantaneous reaction case. So, no A can exist on the catalyst surface, but in this case I have a finite reaction rate. So, some A molecules will be there on the catalyst surface waiting to be converted to A2. So, how would I change my boundary condition? Na would be equal to this one at z equal to delta. Would you agree with that? Okay. So, the amount of the flow, if this is the film, this is my catalyst surface, this is at A moving in this direction, z equal to 0 to z equal to delta. What he is saying is that N A z is going to be equal to K1 double prime C A at z equal to delta. This is what you are saying. Okay. So, you agree with that?
Twice.
Which twice?
NAZ is equal to twice all this.
NAZ is equal to
Twice K1 prime CAZ, that is CA.
why twice? No, the reaction rate is given by this expression. What you are probably doing is I am not considering A2 anymore. Okay. The rate expression is given as this. So, if there is a 2 term that has already been included into K1 double prime. So, this gives you the amount of A converted per unit area per unit time on the catalyst surface. So, I do not need to consider the 2 separately again. So, NAZ at this location has to be equal to the rate at which it gets converted into the product. So, we now know how to handle a fast reaction, what would be the boundary condition for a fast reaction, what would be the boundary condition for a slow reaction. Now, the evaluation of the finding out of the proper proper expression that you can do. There is nothing, no new concepts involved. So, since we have done heterogeneous reaction, let us very quickly do a homogeneous reaction as well. So, A plus B giving AB, that is our system. I have a gas A which is present here, that is slowly getting absorbed at B, and as A starts to diffuse in this direction, this reaction takes place. Explaining one more time, gas A getting solubilized in B and then starts diffusing through the stagnant layer of B, and as it starts diffusing through B, it gets converted into a product by this reaction A plus B giving AB. Now, and let us say this reaction rate is given by K1 triple prime Ca. That is the reaction rate, K1 triple prime, mark this triple prime. Since it is homogeneous reaction, it is all by convention we are taking it to be equal to triple prime. So, we are going to again take a cross sectional area of S and of thickness, let us say delta Z. So, S NaZ coming in at Z minus S NaZ which goes out at Z plus delta Z, plus or minus, would there be a term here, source or sink term? It is a homogeneous reaction taking place everywhere. So, there would be a source or sink term. Is it going to be a source term or a sink term? It is a sink term. So, with a minus 1, so K1 triple prime Ca S delta Z is equal to 0. This essentially is the volume of your control volume. This at steady state would be equal to 0. Alright. So, next step is straightforward, cancel out S, divide both sides by delta Z, and what you have is d NaZ dZ plus K1 triple prime Ca is equal to 0. Okay. Now, how do you solve this problem? If you look at this expression as before, Xa Na plus Nb minus d dCa dZ. If you think of this expression, as I mentioned that in some cases this part would be equal to 0. Would you tell me what I have to assume to make this equal to 0 for this specific case? What kind of constraint I have to impose on A and B such that this is going to be equal to 0? Na equals minus Nb, how do you do that? How do you ensure that Na is going to be equal to minus Nb? There is B is not evaporating, B is simply a liquid and A is a gas which is dissolving at this surface and going in. The B is stationary, B is not moving. You have a cup of water and let us say whatever some carbon dioxide from air is slowly getting absorbed in that air.
So, that absorption is very slow.
That absorption is very slow, or else can I say if the species that I am talking about is sparingly soluble in water. Okay. So, either that rate of absorption is very small. So, if the rate of absorption is very small, then the molecules which are getting absorbed will not be able to move very fast, okay, thereby not causing any bulk flow of B in the liquid as such. So, for a sparingly soluble gas, the amount of flow imposed by the diffusing A molecules will be extremely small. So, only for that case this part would be equal to 0. So, if this part is equal to 0, then I am going to simply substitute this back in here, which would give you the governing equation as dAb d2Ca dz square plus K1 triple prime Ca is equal to 0. So, this would be the governing equation. I do not think we have time today for discussion of the boundary conditions, which we will do in the next class, but what we have seen here is a simple equation results when we neglect the bulk term. It is only diffusion, which is a logical approach to take for sparingly soluble gases in stagnant liquids when the amount of absorption is not much. But the important thing to note here is that this term would appear, homogeneous reaction would appear as a source or sink term, unlike the heterogeneous one, which would come through a boundary condition. So, this is what we have covered till now. We will discuss about the implication of this equation in the next class. Thank you. We are going to start with where we left in the last class. We were discussing diffusion with homogeneous chemical reaction. Now, as we have discussed in the last class, heterogeneous reaction takes place only at a specific location, most commonly on a catalyst surface, whereas homogeneous chemical reaction takes place throughout the medium. And we are going to deal with such a reaction where the reaction takes place everywhere in today's class. So, for that we have a liquid, let us call it B, in contact with a gas. The gas dissolves in liquid B and then starts diffusing towards the bottom, which is situated at Z equal to L. As it diffuses through the liquid, it undergoes a chemical reaction, A plus B giving AB, and the reaction rate per unit volume is given as K1 triple prime Ca. I would again bring to your notice the triple prime, which is generally for homogeneous reactions. So, it is reaction rate, that means moles per unit volume per unit time. So, that is the reaction rate. Now, in order to analyze such a system with Shell mass balance, what we can do is take a strip of thickness delta Z and find out all the in and out terms along with any source or sink. Unlike the two problems which we have analyzed in previously, in this case we will have to see that whether or not any reaction, that means a source or sink term, present in this control volume. One more thing is, as we have mentioned, that the first aim is to find a relation between NA and NB, or to decide whether or not to include the bulk term, the mass transfer term due to bulk flow. Now, there are several situations which would enable us to neglect this term. It could be a diffusion only process. If it is a diffusion only process, if it is mentioned that it is a diffusion only process, then obviously this term will not be present in the equation for NA. On the other hand, several other possibilities exist. For example, this XA could be very small, that means it is a very dilute solution, and if it is a very dilute solution, then you can imagine why the diffusive flow of A through B is not going to impose any bulk flow. The first problem that we have analyzed, that is a gas, a liquid rapidly evaporating, and the vapor that is formed is diffusing through the tube. So, in that case, the rapid motion of A molecules will induce a motion in the B molecules as well. So, if that is not the case, if it is a very slow diffusion case, in that case this term, the significance of this term would be small compared to this term. So, small values of XA, that means it is a dilute solution, or if it is a case of diffusion only process, in those cases these term can be neglected. There exists a special case in which case NA is equal to N minus NB. This is a special case which we will discuss next. dCA dZ evaluated at Z equal to 0 multiplied by minus DAB. So, minus DAB dCA dZ at Z equal to 0 would give you the amount of A which is entering the solution per unit time. It is exactly similar to if you would like to find out what is the heat that is coming in or going out through a surface, through an interface. Its temperature gradient multiplied by minus K at that location. So, here also if you would like to find out the dissolution rate, it would simply be minus DAB dCA dZ at Z equal to 0. So, that is about the main point to remember in this case is if it is a homogeneous reaction, there would be a source or sink term. If it is a heterogeneous reaction, as you have seen in the last class, it is going to come through a boundary condition. All right. So, that is the difference between homogeneous and heterogeneous reactions applicable to mass transfer. This will be later. Now, let us think about a very common problem in chemical engineering. It is diffusion and chemical reaction inside a porous catalyst. We all know how catalysts are important in chemical reaction, in chemical industry and in so many other places. Everyone is trying to make the best catalyst possible. So, how do you quantify whether or not your catalyst is performing properly? Now, if you are making a catalyst, suppose you have to make the catalyst with material A, you can prepare material A in many different ways. So, if I say that this is material A, 1 kg of material A I am giving to you, you make the best catalyst out of it. That means, you are only going to do some structural changes to the catalyst. And in most of the cases, not all part of the catalyst are active, not all points on the catalyst are active. It is only going to have certain active sites. Okay. The catalysts are generally porous in structure. So, you have a catalyst porous in structure, active sites may be within the pores, some of them may be outside as well. So, the active sites are well distributed inside the pores as well as on the outside. So, if you are to make a very good catalyst out of it, what are the changes, what are the steps that you would like to follow? Using your common sense, give me the answer.
Maximum surface area.
Maximum surface area. So, how do you make maximum surface area? That means, probably the better answer would be maximum surface area per unit volume of the catalyst. So, you would like to make it maximum surface area per unit volume. How do you make that? Make it a powder, as small a particle as possible. Now, even after you make a powder, there would still be certain pores inside it. So, not all the active sites will be exposed to the reacting mixture. Okay.